Hello students, in this video we'll discuss a Schwarz Christoffel transformation which maps the unit disk onto a regular polygon. Let's recall the traditional setup. The traditional setup is that if we're given x1 through xn, real numbers, and numbers k1, kn, such that they're always between -1 and 1. And what? You can actually include 1 in some limiting cases, but let's just do this. And the sum, j goes from 1 up to n of kj is equal to 2, right? So this is the setup for the Schwarz Christoffel mapping. Then f prime of z is a z minus x1 to the negative k1, z minus xn to the negative kn, plus b, when you integrate this, gives the mapping of the upper half space onto a polygon with vertices w1 through wn corresponding to these points x, and moreover we know what the external angles are, where the k with external angles k1 pi through kn pi. Those are the external angles. Great. Now what we want to do is, in the case of a regular polygon, we know that all the exterior angles have to be equal, right? For a regular polygon, we need what? We need 2 pi is equal to the sum of all of them, right? So that's going to be pi times k1 plus kn, like that. And all of them are the same, so this is just going to be pi times a common angle alpha times n, right? Times n. So of course the pi cancels out, and that just tells you that alpha has to be what? Alpha has to be 2 over n, right? So these alphas are all 2 over n. So we have our Schwarz Christoffel mapping onto a polygon. All these k1s have to be -2, so this is going to be a -2 over n, -2 over n, -2 over n. Good. Now what we can do is we can say this is our guiding post, and what I'm going to do now is I'm going to construct a mapping not from the upper half space, but from the disk itself, because there's a good way to space those points out, right? So let's let zeta be e to the 2 pi I over n, a nth root of unity. Okay, and now let's consider this mapping over here. Let's consider the mapping f prime of z is equal to a constant a, and then we're going to do what? We're going to do just z minus 1 z minus 1 to the -2 over n, z minus zeta to the -2 over n, all the way down to z minus zeta to the n minus 1 to the 2 over n, right, with a negative sign. Okay, this is going to be a Schwarz Christoffel mapping onto a regular polygon. Great. And so in particular, we get one particular instance of this, which would be very, very nice. Okay, so of course, what do we know? We can multiply all these numbers together, and what are we going to have over here? So up to a constant, this is really just a times 1 minus z to the n to the -2 over n. Beautiful. So now what I'm going to do is I'm going to integrate this and define my mapping, right? So I can consider now f of z is going to be the integral from 1 to z. Now I've set up my limits in the right way, and I'm going to have a d zeta over 1 minus zeta to the n to the 2 over n. It's a map from the unit. I can think of this from the unit disk. I can plug in z equals 1, that's on the unit disk, z equals zeta on the unit disk, and get all those values, right? This maps the unit disk onto a regular N-gon. Okay, now let's analyze this carefully. Let's figure out properties of this regular N-gon. Okay, and it should be clear because I go from 1 to zeta, for example, or those are the roots of unity. I'm going to what? I'm going to basically go around, and the argument of this thing is going to change, right? The argument is going to change on the unit circle, not on the real line, which is okay, right? The branch cuts happen on the unit circle, that works equally well, right? So that's fine. So this gives me a mapping from the disk onto a regular N-gon. Let's find the side lengths. So the question is, what are the side lengths? Okay, excellent. So here we go. So what we're going to do is we're going to integrate from 1 up to this e to the I, e to the 2 pi I over n. So the lengths are going to be of this form. So the integral from 1 up to e to the 2 pi I over n of d zeta over 1 minus zeta to the n to the 2 over n. What we're going to do is make a substitution over here. We're going to let zeta be e to the 2I theta over n, like that. Good. Then what's d zeta? Then this says that d zeta is equal to what? D zeta is going to be 2i over n, e to the 2I theta over n, like that, d theta. Okay, and what's going to happen to my integral over here? So under this transformation, we're going to have what? We're going to have the integral from 0 to 1, 0 to what? Well now, when zeta is equal to 1, theta is equal to 0, so this turns into a 0. When theta is equal to this value over here, when zeta is equal to this value over here, what's theta have to be? Theta has to be pi, right? So I turn it from 0 to pi. Now I have a good length estimator, right? D zeta, so I'm going to have a 2i over n, then an e to the 2I theta over n d theta over what? Over 1 minus, the n's going to cancel out. Now I'm just going to get an e to the 2I theta to the 2 over n. 2 over n like that. And of course, what fact am I using over here? I'm using this fact that I've just multiplied all these things out over here, right? Because this is that's a factorization. Excellent. So now what can I do? So now I'm going to pull this out over here, and what I'm going to do is I'm going to take this and put this in the denominator. So what we're going to do is we're going to take this expression over here, put it in the denominator as an e to the negative 2I theta over n, okay? Which means I can put a what? Which means I can put I have a 2 over n over here and a 2 over n over here. I can put an e to the negative I theta inside there, right? So let's do that. So this is going to be equal to the integral from 0 to pi. Then we're going to have a 2I over n d theta over what? Over e to the negative I theta minus e to the positive I theta to the n to the 2 over n, 2 over n. Like that. Good. That looks like sine, which is very good. So I'm going to pull out the 2 over n. So pull out the 2I over n. And then integral from 0 to pi. Then what do I need? I'm going to plug in a what? I'm going to plug into this denominator. We'll have this one, a d theta, over, I'm going to write like this as e to the negative I theta minus e to the I theta over 2I to the 2 over n. And so what have I added in over there? I've added in a 2 to the n, 2I to the n, so I have to counterbalance that with, I need to put in the denominator a 1 over 2I to the 2 over n, okay? So what we'll do is we'll pull that out as well, right? And you might say this is negative sign, right? Well, there's going to be, so I could put a negative in here and then have a negative 1 to the negative 2 over n. So let me write all those things at once. This is going to be a 2I over n times 1 over 2I to the 2 over n. I'll pull a negative 1 to the 2 over n out, so that I have a 1 over negative 1 over 2 over n, one of those roots. Those are unimodular things, right? Integral from 0 to pi of what? Of d theta over, that's going to be the sine of theta. Sine of theta to what power? Sine of theta to the power 2 over n, like that. Great. Now, I'm going to do the following. I'm going to write this as 2 over n, so this is equal to 2 over n. Then I have a 2 to the negative 1 over n, 2 to the negative 2 over n, okay? And then I have an I have 3 terms over here. We have an I, an I to the 2 over n, and then a negative 1 to the 2 over n to the negative 2 over n, like that. And this is a unimodular number, right? Integral from 0 to pi of sine to the negative 2 over n of theta d theta, right? And so, of course, unimodular, well, what's this expression over here? So I have 2, which is like the same thing as 2 to the n over n, and then that's times 2 to the negative 2 over n. So that's going to be a 2 to the n minus 2 over n. So what's the length over here? So the side length is just the overall length of this the overall modulus of this integral over here. So this is a unimodular thing. That's not going to contribute at all, right? Because it's a modulus one thing, right? So the side length is going to be what? The side length is going to be 2 to the n minus 2 over n, great, over n. And then what? And then the integral from 0 to pi of the sine of negative 2 over n theta d theta. Now, of course, we can evaluate this in terms of the beta function, in terms of the gamma function, but suffices to say that this expression over here, we have seen this before with other Schwarz Christoffel mappings over here. We've seen in other instances, we're going to get these special integrals over here that we can't evaluate in terms of ordinary functions. So in this instance, we need to use the beta function or the gamma function. To further simplify this, let's just leave it like that, right? So classically, you've seen in all sorts of books on control mappings, you see this expression over here for the side lengths, right? And so with this particular choice of Schwarz Christoffel mapping over here, this beautiful choice, I can map the disk onto a regular polygon with these side lengths. So if you want to pick your favorite side length, a side length L, you basically have to take this transformation over here, scale it by that number, right? And then multiply by L. And that will put you into the right framework for a polygon, a regular polygon whose side lengths are L. And you know by this construction that all of the exterior angles are the same, so all the interior angles are the same, and they all match up perfectly, right? So in other words, this will give you anything. Now, we've seen in previous videos that this is not the one we choose for like a square or for an equilateral triangle or for a square. You can use other symmetries of those more simple mappings and maybe move one point to infinity. All the points we've chosen here are endpoints. So I'm taking finite points. So infinity is on one of the side lengths. The point infinity is on one of the side lengths of that polygon, right? And so that's the key feature of this argument. But you can use the symmetry in a lot of other ways to sort of move from the upper half space to the disk, which is a great advantage. We get a nice compact formula for the mapping of the unit disk onto a regular polygon. Thank you very much.